Hello, y'all. How y'all doing? This is Darryl Jr. with an impromptu session of Realizing the Shape, number 39. And actually, need to update my topic title. That's actually going to be Sunday. Are flattered believers dishonest? It's going to be Sunday. I mean, we should make that self-deceptive. But today, I want to talk about my favorite satellites because I think they are a great feat of engineering. And let me pop out my chat here. I thought I had already updated this link, but it's not showing properly. Let's see if that works. It's awesome. Give me a moment. I'll show some web pages. Once I get this chat working, saying live chat is unavailable for some reason. But that doesn't get fixed. I guess we'll have to be without chat for a while. Hmm. Well, no chat showing at the moment. Maybe I'll just input the window itself up in there and do it that way. Boom. That's what I'll do for now. Awesome. So starting with my favorite satellite. My favorite satellite would have to be the Himawari because it's just absolutely awesome. So let me show this page here. Boom. So as many of you know, the Himawari satellite is a satellite that's about 22,000 miles away, or being on the uh, geocentric orbit over Japan, Australia, that side of the planet. Now, one thing that I think a lot of people don't know, it doesn't take actually one picture. Something that was pointed out to me by Fight the Deception. It actually makes a scan over 10 minutes of the Earth, every 10 minutes. And reading farther, I see that it actually makes scans in several different bands. So it looks like it has 16 different bands. Oh, look, is this thing showing? There we go. Now it's showing. Let me see which one of these is not locked for a moment. Okay, there we go. So let me expand this so y'all can see it. So it actually takes images in three different bands, and the color image of the Himawari are derived from composites of three different visual bands: blue, green, and red. So it takes the blue band, the green band, and the red band, and takes those separately, then puts those together to make the color images. So I think that's pretty cool. Um, it's utilized for both meteorological and aeronautical functions. And this image here shows how it puts the data together or captures the data that makes the image. There's a little 2-minute video here, and this is on the actual Japanese satellite for the Himawari, the Japanese Meteorological Agency. So basically, it breaks it down like this over the course of 10 minutes. Now, one unique feature about this satellite, they actually made a new piece of technology for this satellite called the Advanced Himawari Imager. This thing is huge. So if you look at this first image here, right here, you can see how it's pointing to the Advanced Himawari Imager, and it's pointing to this little camera opening, lens opening type section right here. You can see this little section. You can kind of tell the shape, and this right here is what that's pointing to. So this is this right here. So this thing is it's apparently pretty huge. This is another angle. And I found another website here, if I could find it, that showed the launch. And we don't come to those satellites a bit later. Right here. And you notice it's wrapped in gold foil, just like what Loken found that day. The fact that he uses this certain gold material to protect the satellite when it goes into outer space, which is the aluminized polyamide. So you can see that the satellite is wrapped in what apparently is aluminum polyamide, which makes the very obvious gold foil looking wrapping on it. So I think it's pretty cool. So here again you can see the opening, the aperture for where the AHI takes images of the Earth. This is the device that actually scans. Let's see what this article says about it here. This strike strong winds on at 1 a.m. Eastern Time on October 7th. This is in 2014. Japan Aerospace Exploration Agency successfully launched the Himawari 8 satellite on time to begin studying the weather from space. The launch went smoothly without errors or delays from engine ignition to spacecraft separation. At about 1:18 Eastern Time, the two solid rocket boosters filled with liquid hydrogen and liquid oxygen repellents separated from the vehicle, and soon after, the HIIA, which is the Mitsubishi uh, Heavy Industries HIIA launch vehicle, shed its payload fairing. It was followed soon after by first stage engine cutoff at 1:25 a.m. So one thing I find is quite interesting about satellites is the level of engineering that has to go into it to schedule out each of these different phases, uh, minute by minute, second by second. soon to be located at around 23,922 miles above the equator at 140 degrees east longitude. The Sunflower or Himawari satellite will begin its mission of observing clouds and weather patterns far above the Earth. So that's a bit more than 22,000. It's 23,922, according to this article here. Derived from the originals at of geostationary meteorological satellites, Himawari 8 is to observe our planet's weather pattern from orbit as part of the World Weather Watch project of the World Meteorological Organization. The images taken over the East Asia and Western Pacific regions by these satellites are then used for weather forecasts within the media as a means to prevent disasters in those areas. The goal of the satellite is to provide more meticulous observations and disaster preparations. Equipped with cameras dubbed Advanced Himawari Imagers, the satellite's color, high-resolution images will be sent through an internet cloud service to Japan's National Meteorological and Hydrological Services. The HIs are equipped with 16 observational wavebands, 3 for visible light, 3 for near-infrared light, and 10 for infrared light. These images work by moving internal scanner mirrors starting north and moving east to west. So this is the scanning process. These imagers, the advanced Himawari imagers, work by moving internal scanning mirrors starting north and moving east to west. So this confirms what Fight the Deception pointed out here. Even though this seems to be west to east, could be a typo on the site there. But this is the scanning process. And it should take 10 minutes for it to complete. So it looks like it's a bit sped up there, of course, to let us be able to view it in a few minutes. But this whole process for this whole face of the globe should take 10 minutes. The target area is scanned by the full disk within the device and can be moved by changing the direction of the mirrors. As such, the light gathered by these mirrors are absorbed by the 16 wavebands before being turned into electrical signals transmitted to ground stations in Japan. Within just a 2.5-minute interview, the 7,716-pound Himawari 8 is able to scan all of Japan in a series of images. Observations are made by Himawari and the data is sent back to Japan Meteorological Agency every 10 minutes, opposed to its predecessor's interval of 30 minutes between observations. This allows for more accurate data for a quick reaction time should a future disaster such as a typhoon be spotted. The images used within Himawari are based on the Excels. So you can just skip through this a bit. Aside from improved imagery, this mission will also introduce the Himawari cast service, which allows NMHSs to receive images taken by satellite through a communication using digital video broadcasting satellite second generation. Awesome. So this process here is done by mirrors apparently. So at first I was actually thinking that they actually moved the camera some kind of way, like there was an engine or a motor moving the camera back and forth, but really the aperture of the camera must have the whole Earth within its view, but the mirror moves to capture that certain area in sequence, uh, while the receivers capture that data. So that's pretty cool. The target area is scanned by the full disk within the device and can be moved by changing the direction of the mirrors. I wonder how many mirrors it uses because it says mirrors. Now, one interesting thing is the quality of images this thing takes. So let me pull that up real fast. right? So this is the NOAA.gov site, National Oceanic and Atmospheric Administration. But they have a section in their site that captures data from satellites. So let's see if we can find some recent images. Too bad this thing doesn't capture images from outside of the globe because it seems like there's a storm going on in New Orleans. So this is one from not too long ago. I don't know if this is Eastern time or not. Well, I guess it depends on where the NOAA.gov is, probably that same time zone. But this is the most recent image taken. So what's pretty cool is how they're able to take this data from the satellite and make this image for us so quickly. So of course it's nighttime here, so it's daytime over on that side of the planet, which is why we can have daylight there. So this is pretty good imagery, pretty good detail. Might even make this image my background. That's what I'll do. May do that later though. I'll just put that background there for now. I have a rotating background there already. Let's take a look and see if my default chat is working now. So it looks better. See what it looked like 12 hours ago. So let's go to 11 a.m. Maybe to find one for 11 a.m. Here we go. So of course our daytime is their nighttime, so not able to see anything, but still just wanted to see what it looked like. Pretty neat. Hmm. And one thing I noticed here, do you see how the matter of fact, it's gonna take a while to do this, isn't it? I was thinking about downloading a lot of these images and doing basically a time lapse. One thing you can see though, you notice how when we get to this image right here, how we can still see some sunlight. That's because this part of the planet is still leaning towards the sun because we're still in the sort of summer spring area for the northern hemisphere. Therefore, the orbit of the Himawari is basically on an incline relative to the ecliptic, and thus we're able to see some sunlight. That's how the northern hemisphere and the Arctic will have that 24-hour sunlight up there in the middle of their summer. It's pretty cool. So the only time the Himawari will have a full dark view of the Earth will be during spring and fall when its orbit will have it at the equator, which will place it in the direct center on from the opposite side of the sun. That's pretty cool. right now in the middle of summer, so it'll uh, it'll capture daylight. Always at the top. See what it looks like in March. Drag one up by mistake. Let me see here. It's amazing how these images are. There we go. So in March, as you can see in spring, you can get an almost full blackout of the Earth right there, because the way the angle of the planet is hitting, the Himawari is directly opposite the sun, so it's catching the full black side of the Earth. I think that's pretty cool. Now, here's another way that you can get some images. There is a rapid imagery, a rapid scan. You can pick the full globe. You can pick just the Japan area. This is also from the Japan Meteorological website. I think it's pretty cool. Now you see infrared here. We talked about the 16 bands, and as we read in the article, there's 3 light bands. I believe that was the red, green, and the blue. 3 near infrared, and then 10 infrared. 6, 7, 8, 9, 10. So 5 here, 5 there at all those bands. And it uses the infrared. That's how it actually determines cloud and weather. Infrared imagery captures infrared radiation emitted from clouds, land, and the atmosphere. High altitude clouds are cold and appear white in infrared imagery, while low altitude clouds and fog are hardly distinguishable from land, as high altitude clouds may be either well developed thunderclouds or clear day cirrus. Areas appearing in white are not necessarily associated with rain. The spatial resolution of infrared imagery is 2 kilometers at the sub-satellite point. So it uses infrared to determine, you know, uh, very little clouds, no clouds, or very dense clouds. And that's how it helps to get information about the weather. So it's pretty cool. Uh, Now, the data processing side of it. MSC computer systems processed observation data from the Himawari 8 and 9 and the NOAA and METOP polar. So this station does both geostationary and polar orbiting satellites, along with other data such as NWP output. These data are used for various purposes, such as converting observed data into images. I imagine like the ones we saw on the NOVV site, monitoring sea surface temperatures and yellow sand events, and determining the characteristics of atmospheric flow. The Meteorological Satellite Center receives data from primary and secondary ground stations for pre-processing and uses the information to create Himawari standard data, HRIT files, and edited DCP data for provision users. In the event that the MCS system becomes dysfunctional, da da da. It's pretty cool. All imagery derived from Himawari 8 is distributed to NMHS via an internet cloud service. It's pretty cool. So let me put some links up in the chat so it could be there. This is a link to the simple contrast images. Here is the link to seeing various types of satellite imagery, infrared, real time, and so forth. Information about the bands, the 3 bands that it scans for: red, green, and blue. uh, the near infrared bands, the infrared bands, the video of how it scans. All of this stuff is here. You can get these images from that page. This is the one that talks about the launch of the satellite. You can see another image of it. See, there are pretty much some image sites here, which I think is pretty cool. Now, this page here, this is about the Australian government Bureau of Meteorology. I haven't seen this video yet. So it's also, you can see that familiar image of the AHI, which we saw earlier. We compared it with the full view of the satellite. Same image right here from the Japan site. Oops. Well, I'm going to have to paste another image there, but that's fine. Here we go. Japan and so forth that could use this data directly. Uh, I showed that video the last time where someone went ahead and took direct images from the satellite, compared it to the location, and it was able to show how they was able to predict the weather from it. I thought that was pretty cool. See if I can find that video again. Here's that video right here about Wade's World. So that's pretty cool. Now, my next favorite satellite, because the data is used so much, is the Terra satellite. So this is a satellite that makes the Blue Marble data set. Description: Blue Marble is an incredibly detailed, true color depiction of Earth. NASA is responsible for this data set made from a compilation of satellite images throughout 2001. Most of the information came from NASA's MODIS, the Moderate Resolution Imaging Spectral Diameter, which is attached to the Terra satellite 435 miles above Earth. So this one is 435 miles compared to Himawari's 23,000 miles. It's a big difference. The background image of the land and oceans was created using data from June through September of 2001. This cannot be done in a single day or even a week because on any given day clouds are blocking a significant portion of the surface. The cloud image is a composite of 3 days worth of data. The first 2 days of data were collected in the visible wavelength, and the third day was needed to get a view of the clouds over the poles using thermal infrared imagery. The shading is true color, with the ocean shades of blue, the clouds white, and the land varying from green to brown. The brown areas are the sands of the deserts. The shading of the land was done using a data set compiled by the U.S. Geological Survey's Earth Resource Observation and Science Center. So it is pretty cool. So my understanding is when the uh, Himawari, let's say a part of the Earth is in shadow, it could use this data to fill in those gaps. But I'm not sure about that. I have to look into that a bit farther. But that's what I believe they use it for. Now this is more about how this and other satellites uses the infrared, like the Himawari. Geostationary infrared satellite images are used by meteorologists to determine where clouds are, but more importantly, how the clouds are moving. The infrared IR satellites work by measuring the infrared radiation that is emitted. Because the emitted radiation is proportional to the temperature, the data are converted to temperature values, which can be useful for meteorologists. In comparison to clouds, the Earth's surface, even on very cold nights, is very warm. When there are clouds, they absorb the radiation emitted by the Earth below and emit their own radiation at a much cooler temperature. Any area that has clouds show up cooler than the ground, allowing meteorologists to detect the locations of the clouds. The height of clouds is inversely proportional to temperature, meaning that the tallest clouds are the coolest. It is often the tallest clouds that bring the more severe weather. So this is in particular what I was saying earlier from the other site. So it's pretty cool how it's a pretty simple process, but uh, they make practical use of that data. So I think it's awesome. This is what the Terra satellite looks like. Nice little image of it. Since 1999, and it's in sun-synchronous polar orbit that takes it from north to south on the daylight side of the Earth every 99 minutes. So every 99 minutes, this thing is, so it's, what was it, 435 miles up. It circles the Earth every 99 minutes. Bet it's pretty easy to calculate how fast it's going. I don't feel like doing the math right now though. But yeah, should be pretty easy to calculate though. Nice. There's more of the gold foil, the polyamide. Oh, Let me give y'all their link too. Now my next favorite satellite has to be the Mars orbiter. This is the website about the polyamide, aluminum polyamide, which is pretty cool. Now, the Mars orbiter, one thing I like about that one, the Mars orbiter took this picture right here. So this is what the Earth and the Moon looks like from Mars. I think that's pretty cool. One thing I like about this satellite is the engineering that had to go into getting it where it is. Um, I mean, these people are some amazing scientists, like at NASA and all the space agencies. So to do what they do with these satellites, uh, get them safely past the Earth, past the Moon, um, hundreds of thousands of miles away to different planets, to beyond the solar system, sending back data. I think it's awesome. The Mars Reconnaissance Orbiter Mission Overview. NASA's Mars Reconnaissance Orbiter blasted off from Cape Canaveral in 2005 on a search for evidence that water persisted on the surface of Mars for a long periods of time. Typo. While other Mars missions have shown that water flowed across the surface in Mars' history, it remains a mystery whether water was ever around long enough to provide for a habitat for life. Studying the history of water on Mars, looking at small scale features is pretty cool. So it weighs 4,806 pounds, including fuel. Wonder how much fuel. Electrical solar panels, and it's still ongoing. So, wondering if I can find some information about its the process it went to get out there. We do a search. So this is the page I have right there. Launched. So it's the rocket that lifted it off. 2005. So let's take a look at some of the pictures this thing took. Interesting. So it took a picture of the Curiosity rover from orbit of the planet. It's pretty cool. Hmm. This looks similar to patterns that was on the moon that I saw. But they said it was, well, the one I'm thinking about, can't remember that guy's name, but he showed pictures from from the moon, but it was like a double um, path though. It's very similar though. Mm. New impact of crater. It's pretty devastating. Hmm. So this could be an image of the path that the rover is taking. These double lines here. If I'm understanding this properly. Mars gets blasted with space rock much more frequently than Earth because they are less likely to burn up in its thinner atmosphere. This photo shows several recent impact scars on Mars seen by NASA's Mars Reconnaissance Orbiter since 2006. So, whenever we do get to Mars, generally, we need to make sure that we have enough shielding on our habitats. Hmm. So there's two rovers on Mars right now. Opportunity and Curiosity. Now, if I had to say the other favorite satellites, it'd have to be the Voyager satellites because they're leaving the solar system. At least they've already left the solar system. Voyager 1 reached interstellar space in August of 2012 and is the most distant human-made object in existence. Launched just shortly after its twin spacecraft, Voyager 2, in 1977, Voyager 1 explored the Jovian and Saturnian systems, discovering new moons, active volcanoes, and a wealth of data about the outer solar system. Hmm. You remember one of the Star Trek movies had featured the Voyager satellites. I believe some alien race captured it and improved it and sent it back. This is the article I was reading the other day about the fact that it was checking the magnetic waves and things like that. I would like to find something that shows the actual voyage it took. Interesting. This is an illustration of the magnetic spheres or electromagnetic spheres or bands that we're in. Nice. So apparently the heliosphere, the sun makes this bubble that protects us from probably a lot of other radiation and things that's going on out there. I imagine it's sort of warped because the sun is moving through the solar system as well. But they've already look at this. I forgot that the Voyager satellites took pictures of the Earth too. Left, Voyager launch. Middle, model of the Voyager spacecraft. Right, the first single-frame image of the Earth-Moon system, taken by Voyager 1. So Voyager actually took the first single-frame image, single snap of the Earth and the Moon together. It's pretty cool. I'll put that image there for y'all. I would still like to find. I remember seeing somewhere and this is an image of the gold disc that is put on it. Voyager 1 took the image of Jupiter backlit by the sun and discovered that the planet has a thin ring system. Hmm. Jupiter has rings, but very thin. Oh, here we go. That's what I want to see. So this is its trajectory through the solar system. All right. So this would have taken some tremendous. And by the way, if you haven't signed up already, make sure you sign up for the out-of-body astral projection course I'm offering. Just go to darrylleberryjr.com, DARRYLEBERRYGR.com. You can click courses and classes at the top in the menu, and you should be able to see everything you need to sign up and everything. So imagine the engineering sophistication and the orbital mechanics detailed knowledge that you have to pull this off. So right now they're going by Jupiter. Okay. And they use the gravity of Jupiter, the slingshot. Let me get the link to this thing and bring it full screen. So this is the NASA site. Surprised I didn't subscribe to them yet. So let's check this out again. Right. So they shut off from Earth. Going extremely fast. You're probably getting help from Mars's gravity right now. And this is in June 1978. So this is what it was doing in 1978. And you can see at the bottom the days that's going by. This is literally months right now. So when it originally shut off, it was in August 1977, September 1977, October 1977, November 1977. So this is months. December 1977 is just catching up to Mars, passing Mars' orbit. January 1978. February 1978. It's past Mars. March 1978. April 1978. May 1978, June, July 1978, August, September, October, November. So the speed must slow down. December, wow. January 79, February 79. So right now I use the gravity of Jupiter to help it along, both of them. July 1979, August, October, November, December. So the speed must have greatly, they must have used Jupiter's speed to greatly slow them down right there. So notice that the time frame started to speed up. So the satellites must have slowed down a whole lot and it sped up that part of the journey. May, June, July, August, September, October, November. So now we're in 1981. So you saw that? It used the gravity of Saturn. So Voyager 1 went underneath Saturn and used the gravity of Saturn to pull it and slingshot it back. So now Voyager 1 is on a trajectory outside the solar system. That was awesome. So now it's basically going not perpendicular, but almost perpendicular to the ecliptic. That's some amazing engineering. Amazing calculations. So what they had to do, they had to know the location of Jupiter, use that for a slingshot, and calculate and design these satellites so precisely that they could slingshot off of Jupiter in enough time to catch Saturn in its orbit, and then Voyager 1 can slingshot upward from Saturn. I mean, that's just marvelous engineering. And you can see how Voyager 2 used uh, 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 Saturn's gravity to pull itself along its trajectory, but Voyager used Saturn to sling itself out of the solar system, almost perpendicular to the ecliptic. I actually wondered how they got it out, but I figured they did something like that. So these different grids, these spherical type grids, must be uh, the belts of radiation that is hitting. So now we're in 2010. So now it's going a whole lot slower. It's taking decades, but now this thing is literally exited the solar system and is in interstellar space. That's amazing. Let's see the trajectory of Voyager 2. Here's the Voyager 2 trajectory. Let me get the Voyager 1 trajectory before I forget. So this is Voyager 1. So ironically, Voyager 1 was shut off a little bit after Voyager 2. November 77, December 77, January, February, March, April. So they're going pretty quickly. May 78, June, July, August, September 78, October, November. They must have slowed down a lot. December, probably with Jupiter's gravity. So Voyager 1, whereas Voyager 2 used Jupiter's gravity. Well, both of them actually. I mixed up my planets. So they both slung with Jupiter. Saturn is the one where they're going to deviate. So that's Voyager 1. Oh, I put the wrong one in. I wanted Voyager 2. One moment here. Let's speed up back to where they deviated. So Voyager 2 saw that. So it used Saturn's, whereas Voyager 1 used Saturn's gravity to sling up. Voyager 2 went behind Saturn, used Saturn's gravity like a slingshot to sling it forward. Went to Uranus, used a little bit more of its gravity, went to Neptune, down. And he used Neptune to go down off of the ecliptic. I didn't realize that both of them was going outside the solar system. So this is marvelous engineering, marvelous work. I think I need to up my game, work on my OBE more maybe, do some more exploring, get some more detailed data. So Voyager 1 is going out the exo solar system north of the ecliptic, and Voyager 2 is going exosolar system south of the ecliptic. And Voyager 2 used Uranus's gravity. So I bet they was able to, excuse me, Neptune's gravity to eventually go out the solar system. So I bet they was able to get some good pictures of those planets too. Man, that's some mad engineering. So I have to know. And I wonder if the satellite is programmed to do those moves, or they're actually sending it any kind of correctional data in its journey. Surprised there's been no comments. I think programmed, but I'd like to get the answer. I don't know that they'll answer here, but I'll put it there just in case. See what else we got. Man, over decades, that's some planning. So cool, guys. Those have to be my favorite satellites. Those are, I guess, pretty much the only ones that's doing something very interesting. I guess most of the satellites are just getting weather data with less sophisticated, real color imagery than the Himawari or, uh, you know, sending back weather data and things like that. But cool. Hope you'll enjoy it. Those who may watch this later, I'll probably be on later, looking into something else. In a moment, I'll see if there's someone who may want to discuss uh, satellites or something before I end. One moment here. All right, y'all. Thanks for joining. I'll go ahead and shut the stream down for the moment. Tomorrow, I'll be, if not before, tomorrow I'll be back with uh, moderating a debate between SE Montreal and Sean Hawkins. This is on my favorite satellites, which is the Himawari, Terra, and Voyager. Oh, and Mars Orbiter. All right, you all. You have a nice one.